So, today we will be talking about motion of a charged particle in a magnetic field. So, if you have a magnetic field B, let's start with a constant magnetic field, uniform and constant, does not change with time and in space also. In the region of interest it is uniform. Generally magnetic fields are, it is difficult to produce uniform magnetic field, but in a smaller region you can do it. Okay. So, we assume that we have a uniform and constant. What is difference? Constant and uniform. When I say uniform, that means in the space, the region of space in which we are interested, in which we are working, it is not changing from here to there to there. And constant means look at any point, it does not change with time. So, that is the meaning of constant and uniform. So, once that field is given and is uniform, that means everywhere it is in the same direction and with the same magnitude. So, we can take that direction itself as the z axis. So, no loss of generality, take the z axis along the field direction. In that case, B is the magnitude B and then k cap. Now, if the particle has charge q, mass m, and it is given some initial velocity v, then after some time if you see it will be somewhere else and it will have some velocity. So, let us say that velocity is v, this is at time t. This is at time t. Velocity in general it will have all three directions. So, we write Vx I cap, Vy j cap, Vz k cap. The force F on this charged particle by this magnetic field is q times V cross B, and that is q times V is Vx I cap, Vy j cap, Vz k cap, and then cross product with B k cap, and k cap cross k cap will be 0. So, this term will not give anything, and here it is q into Vx into I cap cross k cap, which is minus j cap, then plus Vy q Vy, and then j cap cross k cap is I cap. So, it is this. So, it is this. So, this is the force, and you can write acceleration also. If you write acceleration, then A, which is dv dt, is F by m. Where is that B? This B is there. So, F by m, and that is equal to q. I can write q outside this bracket, this B, and then divided by m. So, I have written this q, I have written this q, I have written this B, and so that q divided by into B divided by m. Then we have this minus Vx j cap and plus Vy I cap. That is acceleration, that is dv dt. Once again you write this V in terms of I cap and j cap, and what you get is the following: d dt of V, that is dVx dt, and then plus dVy dt in j cap direction plus dvz dt in k cap direction. So, this is this acceleration dv dt we have written in terms of I cap, j cap, k cap, because velocity is vx I cap plus vy j cap plus vz k cap, and this is equal to qb by m. So, qb by m and then minus vx j cap and plus vy I cap. So, vy I cap and minus vx j cap. Now, compare the x component, this I cap here, this I cap here. So, what you get? dvx dt is equal to qb by m, this we will write omega. So, omega and then vy. Now, compare j cap and j cap y component. So, dvy dt, and that is equal to minus omega vx. This is omega, this is minus, and this is vx. So, minus omega vx, this is dvy dt. Now, what to do? You have dvx dt here, but this is a function of vy. So, I cannot take this dt and integrate. Similarly, here dvy dt, and here it is vx. So, one popular method is that you differentiate this first equation. If you differentiate the first equation, what do you get? You get d2 vx by dt square, d2 vx dt square, and is equal to omega, which is constant, qb by m, and vy. So, differentiate, you get dvy dt, but dvy dt is here, dvy dt is here, it is minus omega vx, substitute there. So, this is equal to omega and then minus, so minus this one more omega, omega square, and then this vx. So, d2 vx dt square is equal to minus omega square vx. Now, you have vx this side, you have vx this side, and this differential equation can be solved. Similarly, if you differentiate the second one, dvy dt, so you get d2 vy dt square, and then equal to minus omega, this minus omega dvx dt. So, dvx dt, and that is equal to minus omega dvx dt, you write from here omega into vy. So, this is omega and into vy, d2 vy dt square is equal to this. Now, this equation you remember, simple harmonic motion where force is proportional to the displacement and opposite in direction. So, there you have this type of equation, d2 x dt square is equal to minus omega square x, where omega is square root k by m, spring constant here, and this is the equation of SHM. And you can do some algebra, and you know the solutions. It is x is equal to some a sin omega t plus phi. So, using this you can write what is Vx and what is Vy with some arbitrary constants. But I want to introduce yet another algebraic method. It is very interesting and you will enjoy it, and that is we solve this equation to get Vx and Vy in a slightly different manner. So, we have these two equations, dVx dt and dVy dt. You multiply the second equation by the quantity I, and this time it is not I cap, it is only I. And what is that I? That I is square root of minus 1. Okay. So, multiply the second equation by this I and then add these two equations. So, on the left hand side what you get, d dt of Vx plus I Vy, d Vx dt plus I times d Vy dt. So, it is d Vx dt plus I times d Vy dt. This is on the left side, and right side you get omega Vy here, omega Vy here, and then minus I times omega Vx. Okay. This I gets multiplied here also and you are adding. So, omega Vy and minus I times omega Vx. So, that is on this side. So, this is d dt of Vx plus I Vy, and that is equal to, let us take minus I omega common, minus I omega common. So, from this side you will only get Vx, and from this if you take minus I omega common, you get I times Vy. Verify, multiply this and see if you are getting this. You have I omega minus I omega Vx. So, minus I omega Vx, and here second term, this I multiplied by this I is minus 1. You have another minus here. So, that is plus 1, and then it is omega times Vy. So, omega times Vy. So, this is it. Now, write capital V as Vx plus Iy. Call this quantity as capital V. It is some kind of a velocity, but it is a complex velocity, capital V, and this side it is. So, this is d dt of V. So, if you write this side is d dt of capital V, and that is equal to minus I omega capital V. This is capital V. Now, this equation is very simple to solve. You only have to write this V on this side, dV by V is equal to minus I omega dt, and therefore, ln of V, the integration, this is logarithm on the base E, log on the base E. So, this is written as ln. So, it is this, and here it will be minus I omega and then t and plus some constant here, and that constant can be written from this side also, and finally, you get V is equal to V naught e to the power minus I omega t. Right, very simple equation to integrate. dV by V will be log V, and then you will put some initial value and current value. So, that will give you ln of V by V naught. V naught is the initial value, and then this side it will be this. When you remove this ln, that becomes e to the power. So, this is the solution. This is the solution. V is equal to, what we do not know is V naught, right. This is at time t, Vx and Vy at time t, then this time t is here. This V naught is the value of this velocity, complex velocity, when t equal to 0. What is this V naught? At t equal to 0, put t equal to 0. If you put t equal to 0 here, this will be 1, e to the power 0 is 1, and therefore, V is capital V naught. So, at time t equal to 0, what is Vx and what is Vy? From there you construct how much is this capital V, and that will be this V naught, and the velocity is obtained. So, let us take some example. Let us take a concrete example. Suppose we have a uniform magnetic field, and initially the charged particle is somewhere, and we give it an initial velocity. So, suppose your B is, as we write, B k cap. So, suppose this is the region, in which I have this magnetic field, uniform magnetic field. in k cap direction. So, this is k cap direction coming out of the board. So, we can denote it by this dot. So, everywhere you have dot dot dot, that means everywhere you have this magnetic field coming out of the board. And then the charged particle, suppose at t equal to 0, the charged particle is here and is having a velocity v, some v naught, let us say v naught. The charged particle is given a velocity v naught in some direction which is perpendicular to the magnetic field. So, magnetic field direction we have committed, it is z direction, and perpendicular to that is this xy plane. So, in this xy plane perpendicular to the magnetic field, we have given an initial velocity v naught to this charged particle of charge q and mass m. So, that is the situation. Now, we can as well take x axis along this direction, whatever direction is the initial velocity, we choose that as the x axis. So, this is x axis and perpendicular is y axis. So, that x cross y or I cap cross j cap is k cap. So, this is the situation, this t equal to 0, this is at t equal to 0. Now, we want to know at a later time t, where is the particle, what is its velocity, right. So, we already have this equation, capital V, which is complex velocity at time t, is equal to this initial complex velocity v naught e to the power minus I omega t. So, what is v naught here? What is v naught here? V naught is V x plus I V y at t equal to 0. V y is 0 and V x is v naught. So, this v naught is equal to this small v naught, which is real. This is the velocity, this is the velocity we have given to the charged particle. So, that v naught comes here and that is it. Okay. So, our equation is capital V is equal to this small v naught e to the power minus I omega t, and I am very sure you know this equation, e to the power I theta is cos of theta and plus I times sine of theta, right. This is very useful and common equation, e to the power I theta is cos theta plus I sine theta. If you write minus here theta, if you replace theta by minus theta, then you can also write e to the power minus I theta is cos theta minus I sine theta, because cos of minus theta is same as cos theta and sine of minus theta is minus sine theta. So, it is this. So, use this thing here. What do you get? Capital V. What is capital V? Capital V is V x plus I V y at time t is equal to V naught times e to the power minus I omega t, e to the power minus I theta is cos theta minus I sine theta. So, this is cos omega t and minus I sine omega t, right, e to the power minus omega t, e to the power minus I theta. So, it will be cos of omega t and minus I sine of omega t. Now, compare the real parts and compare the imaginary parts. So, you get V x is equal to V naught cos omega t and V y is equal to minus V naught sin omega t. So, we have solved our equations. The more popular common method, as I said, you differentiate one equation and then use the second equation, you get a second order differential equation, d2 Vx dt square equal to minus omega square Vx, and similarly for Vy. Here we have avoided that second order differential equations, and only first order differential equation is solved and we get our results. Okay, so this is about velocity. And what about position? What about position? So integrate this Vx is dx dt is equal to V naught cos omega t, and therefore you can write dx is equal to V naught cos omega t dt. Integrate, you get x here, and here you get V naught integration of cos its sine, so sine omega t, and divided by this omega, you know all these things, and plus some constant, right. If you this t you have to integrate with respect to t, here it is omega times t, so you have to divide by omega, and then cos becomes sine, so sine omega t by omega this. Now what is this c? At t equal to 0, what is x? At t equal to 0, what is x? We have chosen our origin at the position from where this particle is given this initial velocity. So x is 0. So at t equal to 0, x is 0. So t equal to 0, x is equal to 0, that gives you c equal to 0. So x is equal to V naught by omega and sine omega t. So this is x, and similarly try to find out y from here. Vy, what is Vy? Vy is dy dt, and that is equal to minus V naught sine omega t. So you write dy is equal to minus V naught sine omega t, and then dt, and integrate. When you integrate the two sides, you get y here equal to minus of sine omega t. Integrate, you get cos omega t divided by omega, right. Sin x, when you integrate, you get minus cos x. So minus of sin x is here, so you will get cos x, but then it is not x, it is t, and it's omega t here, so it is cos omega t and divided by this omega plus some constant. What is this constant? At t equal to 0, what is y? At t equal to 0, what is y? Once again, since we have chosen our origin at that initial instant where the particle was there, so y is also 0, so y is equal to 0. But then this c is not 0, this is 0, y equal to 0, t equal to 0, cos of 0 is 1, cos of 0 is 1, V naught, we have missed this V naught, okay. So at t equal to 0, y equal to 0, so y is equal to 0, t equal to 0, cos omega t is 1, so it is V naught by omega and plus c. So c is equal to minus V naught by omega, and hence this y is equal to V naught by omega cos omega t and minus 1 minus V naught by omega. So minus V naught by omega, this is y. What we have gotten at time t, what is the velocity we have gotten? All three components, the x component, the y component, and the z component. We have z component is 0, because in that initial equation where you can see that dvz dt is equal to 0, because force did not have any z component, k cap cross k cap was 0. So this is 0, so Vz is constant, and if initially there is no Vz, if initially Vz is 0, Vz will remain always 0. So, Vz is 0 all the time, and if you integrate this, what you get is z is equal to constant. Vz is 0, dVz dt is 0. So, z is just a constant, and if z is constant and initially z is 0, initially we have taken the origin here. So, that z will remain 0 all the time. So, we have gotten all three components of velocity. Velocity Vx is here, Vy is here, and Vz is 0. Then we have gotten all the three components of position, x is here, y is here, and z is 0. So, from this we can find anything about the motion of this charged particle, which is initially given a velocity perpendicular to the magnetic field. So, we will do the geometry of this in the next lecture.